Look up at a thunderstorm, and the violence seems to come from nowhere. In reality, these clouds erupt to mark the exact physical coordinates where massive, invisible thermal boundaries have collided. To understand what triggers these hazards, we have to look past surface-level observations and decode the precise three-dimensional mechanics of the atmosphere. This starts with the foundational entity of meteorology, the air mass. These are vast parcels of air that overlie a surface long enough to absorb its specific heat and moisture properties. A polar maritime air mass originating over the northern oceans will be heavy, cold, and moist. In contrast, a tropical continental air mass forming over a desert will be exceptionally warm and dry. Aviation weather hazards emerge from the strict mechanical interaction between these colossal thermal blocks as they shift vertically and collide horizontally across the globe. The properties of an air mass shift the moment it begins to move away from its point of origin. This diagram illustrates a cold polar air mass moving equatorward. Heated from below, lower layers destabilize, expand, and rise. Conversely, as tropical air travels poleward, the cooler surface draws out heat, causing it to settle and compress into a stable state. This shows convergence. Surface winds flow toward a low-pressure zone, forcing colliding air violently upward. As it ascends, it cools, condensing moisture into heavy precipitation. Conversely, divergence in high-pressure systems causes upper-level air to sink, subsidence, spreading outward and dissipating clouds. This descending air compresses and warms as it loses altitude, creating exceptionally dry and mechanically stable flight conditions. The fundamental trigger for either clear skies or storm hazards is the vertical direction the air is forced to travel. When two opposing air masses physically collide at the surface, they create a frontal boundary. A warm front exists where a warmer, lighter air mass gradually replaces and overrides a cooler air mass at the surface. This cross-section displays warm front geometry. The shallow boundary rises at a 1 to 150 ratio. Because advancing warm air slides up this gentle ramp, lifting is slow, creating a massive shield of stable stratiform clouds extending hundreds of miles. As rain falls from the warm air into the trapped cooler air below, it can saturate the lower layer, generating thick precipitation-induced fog and reducing visibility at the surface. If the underlying cold sector is below freezing, that liquid rain becomes supercooled and instantly freezes on contact with an aircraft, causing rapid structural icing. Pilots will observe steadily falling barometric pressure that stabilizes upon passage, alongside rising temperatures and a veering wind direction. The shallow geometry of a warm front guarantees prolonged, horizontally expansive weather hazards that can trap aircraft under a persistent layer of clouds and ice. A cold front operates through a heavy, cooler air mass, aggressively undercutting and displacing a warm air mass. This compares boundaries. Ground friction creates a steep wedge with a 1 to 50 slope. This incline shoves warm air straight up, creating rapid, intense vertical lifting packed into a narrow 50-mile band. This lifting generates severe cumuliform hazards, including heavy hail, isolated thunderstorm cells, and rapid onset squall lines. The immense energy released by this lifting builds towering cumulonimbus structures that punch through the atmosphere, expanding into the massive anvil clouds seen here. At the boundary line, pilots face severe low-level wind shear and extreme turbulence due to the violent exchange of vertical and horizontal momentum. Instrument indications include a sharp pressure drop, followed by a rapid rise, accompanied by a sudden temperature plunge. By force-multiplying vertical lift through its steep friction slope, the cold front condenses atmospheric energy into narrow, violent bands of weather. Cold fronts travel across the Earth's surface significantly faster than warm fronts. When a fast cold front catches a slow warm front, it creates an occlusion, pinching warm air aloft. This creates embedded thunderstorms, violent cumuliform cells hidden entirely inside massive, benign-looking stratiform cloud banks. These individual fronts are the trailing arms of a larger engine, the cyclonic depression or low-pressure system. Lows drive these systems through surface convergence, pulling air inward and forcing it to rise and destabilize. The contrast is the anticyclone or high-pressure system, defined by massive slow subsidence. While highs generally bring clear skies, the sinking air compresses and warms, often creating strong temperature inversions. These inversions trap dust, smoke, and radiation fog close to the ground, creating a ceiling of poor flight visibility that can persist for days. Fronts do not exist in isolation. They are merely the connective tissue between the massive engines of high and low pressure. For a pilot, a standard meteorological chart provides the essential blueprint for a flight briefing. These symbols, the barbs and semicircles, function as top-down blueprints, encoding the specific three-dimensional geometry of the atmosphere onto a two-dimensional plane. Identifying a specific boundary allows you to visualize the invisible physical slope of the air mass. The semicircle indicates a long, shallow ramp. The barb marks a steep, blunt wedge. Knowing this 3D geometry enables pilots to accurately predict the aerodynamic hazards awaiting them, from freezing rain to low-level wind shear. True meteorological mastery is found in this translation, viewing a flat map and seeing the three-dimensional architecture of the sky.